evening. My name is Jacob Bowen. This is my video presentation on airfoil design. Airfoils come in a few basic shapes. The main two in use today are symmetrical airfoils and cambered airfoils. Symmetrical airfoils have a same shape bottom and top. The camber on top of the wing is the same as the camber underneath the wing, and therefore they don't generate any lift because they don't generate dynamic pressure at a zero angle of attack. However, when you increase the angle of attack, dynamic pressure starts to build. The under surface of the wing, the lower surface of the wing generates positive lifting force, positive pressure, and the upper surface generates negative pressure, which helps lift the wing up into the air, where the center of pressure is going to be further forward on the wing, and the fall off of pressure generated is going to be rather steep. The rear of the wing is going to generate less pressure than the front of the wing, and where it impacts, there's going to be a rather equal dispersion of pressure around the curved surface, or even if it's a flat surface, around the leading edge surface of the wing. On the other hand, a cambered airfoil generates lift even at a 0 degree angle of attack. However, as you increase that center of pressure, just like the symmetrical airfoil design, moves forward. However, there's a more even distribution of negative and positive pressure on the upper and lower surfaces of the wing due to the camber of the wing, and there's a much more linear fall off of pressure generated by each surface of the wing, as the entire wing is helping to generate that dynamic pressure difference. So this means that the higher the angle of attack, the more forward that center of pressure is going to be. But due to its ability to generate lift at 0 angle of attack instead of needing an angle of attack to generate lift, a cambered airfoil actually generates a greater amount of lift. However, a symmetrical airfoil has its benefits when used in certain applications, such as sport planes, which need to be able to generate an equal amount of lift, whether inverted or in straight and level flight normally, or on some high-powered helicopters. Rotors used in those designs are symmetrical, which allows the helicopter to generate 0 lift while being at high RPM settings before taking off. A cambered wing is designed with an upper camber that is very large compared to the lower camber of the wing. There's a large difference, which helps generate that large dynamic pressure difference, generating higher pressure air down here and relatively lower pressure air above the wing. From the leading edge of the wing to the trailing edge of the wing, that line straight back is called the chord line. This chord line is what we reference when we reference relative wind for angle of attack. It's relative wind to not the relative camber on the bottom of the wing, but it's relative wind relative to the chord line of the wing. The camber line, this is very exaggerated here, but the camber line of the wing is just the mean line of camber tracing the wing. And then the thickness of the wing is just the thickness of the wing at any given point along its surface. Here I picked just the thickest part of the wing, which would be here the biggest difference between that lower camber and upper camber. As we're talking about this this chord line. Flaps help increase chord line. They also help increase camber line to help an airplane generate more lift at a lower airspeed, so it allows the wing, or allows the plane to stall at a lower airspeed, decreases the stall speed of an airplane. The change in chord line by extending the chord line of the wing, so flaps will bring the chord line down, as you can see here, the leading edge versus the trailing edge. And again, this is a very exaggerated example, but the leading edge of the wing to the trailing edge, that chord line is much longer here than it would be just if the trailing edge were back in its normal position, which increases the surface area of the wing, increases the amount of air deflection that the wing produces. It deflects greater amounts of air. This increased chord line also redirects the flow of air, so this chord line is more in line with the relative wind at a higher angle of attack, allowing airflow to be laminar airflow to be generated for longer. And then the camber of the wing, the increased camber line of the wing, sorry, something in my throat, also helps with that increased deflection of air, as there's a greater angle at which air hits. So not only is it got a greater surface area, the relative wind is more in line now with the chord line of the wing, but that relative camber, that camber line of the wing is greater, and also helps add to that greater deflection of air. Here we see the four main types of flaps on a wing. Plane flaps, which are what you see on most general aviation trainer aircraft, just extend the trailing edge of the wing down into the wind. Split flaps leave the upper camber surface of the wing alone, just to deflect that lower cambered surface of the wing down into the air. Both of these work in a relatively similar fashion to one another by just increasing that camber and that chord line and directing more air down, so that way the wing can continue to generate lift at that lower airspeed. Slotted flaps move the back that back trailing edge, that back section of the wing down a bit further, creating this air gap here, which allows high pressure air to escape up over this, which increases the velocity of the wind going, or the air going over the top of the surface, which helps allow this trailing part of the flap to actually generate a little bit of lift on its own. And then also by allowing that high pressure air to go through, it creates less of a drag barrier than your plane or split flaps do. They generate a good amount of drag as well. Fowler flaps are like slotted flaps, where that rear section of the wing extends downward, except they do not, in a base Fowler flap configuration, allow for that high high pressure air to escape through in as much volume. It allows for some separation, allows for some air to flow through, but not as much as a slotted wing configuration, which actually is why slotted and Fowler flaps have been combined on larger aircraft, allowing the benefits of the Fowler flap, which is relatively low amounts of drag and a great increase of lift at a low angle of attack. Plane flaps and split flaps require a higher angle of attack to be more effective. Fowler flaps do not need as high of an angle of attack to be effective, so it allows a higher maintained airspeed for longer, and then a lower angle of attack so that plane or the jet can maintain relatively level to the relative wind. And then they increased the effectiveness of Fowler flaps by also adding a slotted feature to them, so now they're multi-stage flaps that come down, and in that configuration they can have higher angles of attack while generating relatively low amounts of drag, as high pressure air is allowed to go around that flap. Continuing with aerodynamic wing design, something that has been used to help increase the generation of lift by an airfoil or by an airframe itself is canards. Canards are fantastic devices when used correctly. They have the ability to generate lift on the nose of an aircraft, positive lift on the nose of an aircraft, instead of your typical tailplane section, which generates a negative lift component. It generates downforce instead of lift. This positive lift that canards are able to generate helps reduce the load, the wing loading experienced by the main wing of an aircraft, which also induces less drag because there's less downwash, and the downwash from the main wing also doesn't interfere with the lift capability of a canard, as the canard's placed in front of the main wing section. Canards also help to naturally reduce stalls. A canard is designed to stall first before the main wing, which drops the nose of an aircraft, allowing it to build speed faster to then regain control and be able to pull out of the stall. However, canards have to be properly balanced with the amount of lift that they generate compared to the amount of lift generated by the main wing. This means that in most situations, the pitch control for that aircraft is limited, so that way the angle of attack of the canard can't be exceeded too rapidly, but also meaning that you have greater takeoff lengths, and then also not as much pitch control, which can lead to some pitch stability problems. And then also, if improperly balanced with the main wing can actually stall before the canard, which means that the canard is still generating some lift, which raises the nose of the aircraft momentarily in a stall, which causes a stall to deepen and get worse before the canard exceeds its critical angle of attack, and control can be regained there. So that was my basic presentation on airfoil design. Thank you for watching, and have a great night.